Hi, I am Abhinandan Bhattacharya. In this video, we will discuss or formulate a strategy for finding Lagrangian of a system and also give few examples. So finding Lagrangian is very important in the context of many competitive exams, as well as if you know how to figure out the Lagrangian, that will help us to find out the equation of motion for some complicated systems which may be difficult to find using the Newton's equations of motions. So let's explore that now. Is Lagrangian. Lagrangian is given by T minus V, where V is the potential energy, and it can be expressed as a set of coordinates which we call as generalized coordinates, and we will come to that. T is the kinetic energy, and it is a function of generalized velocity, which is time derivative of the earlier one. Now let's take a look on what is generalized coordinates. So these are actually a set of minimum number of independent variables with which one can describe the state or motion of an entire system. So let's take a look by doing some simple examples. So suppose this one, where the mass is moving along this direction. So it's a 1D motion. So if we know the x coordinate at a given instant, we can figure out the entire motion of the system. So here x is good enough to do the or to describe the entire system. So x is our generalized coordinate here. Now in this problem, this object is moving along the circular path of radius a. Now to describe this object, what are the minimum variables required? So we need to figure out that one. So we can first look at what is the position of that object. So here the x and y. Now I can write x as a cos theta, y as a sin theta. And since a is constant, therefore x and y both can be expressed only in terms of theta, and theta is an independent variable. So therefore this motion of this entire object is actually depending on that, or not depending, can be expressed by only theta. So theta is our generalized coordinate. So in these two examples we have found only one generalized coordinates, but there can be problems or complicated situations where we will find more than one generalized coordinates, and we will see that in our next problems. Okay, now if we know the generalized coordinates, that will help us to figure out t and v, and it will give the Lagrangian. If we combine all this information, that will give us this equation of motion, and this is equivalent to the equation of motion that we figured out from the Newton's law. And one point I want to mention, for finding equation of motion from Newton's law, we are concerned about what are the forces acting on the system, but here we are actually dealing with only kinetic energy and potential energy, and these are the scalar quantities. Sorry, these are the scalar quantities. Therefore, our problem of finding equation of motion becomes a scalar problem, not a vector problem, and that can be a very convenient situations for many complicated problems. And another point is that now one can figure out Lagrangian just by properly knowing the coordinate of a given object or a given system or a set of objects. So if we know coordinate properly, we can figure out the Lagrangian, and that will demonstrate in our next few slides through few problems. And here we are concerned about only finding the Lagrangian. Once we know the Lagrangian, finding this one is a piece of cake. So here we'll only find the concern on finding the Lagrangian. So let's take few problems. So let's start with our first problem. In that problem, we'll see a pendulum will move along a elliptical orbit. So in the figure, this is the elliptical orbit, and a point object is sitting on it, which is massless, and that is attached to a pendulum of bob mass m. Length of the string is L, and it makes an angle theta at a given instant with that point object. And this entire system is moving in that orbit with an angular velocity omega. Now we need to figure out the Lagrangian of the system, and we consider O as the origin. This is the positive x-axis, this is the positive y-axis. And for finding Lagrangian, we need to figure out the coordinate of this object of mass m. And before that, we need to figure out what is the coordinate of this point object, and using that we'll come to mass m. So let us consider at a given instant, this is the angle phi it makes with the major axis. This point object makes an angle phi with the major axis at a given instant of time, and using that we can find its coordinates. So this is the x coordinate x0 and this is the y coordinate y0, and we can write this as a, in terms of phi, x0 is a cos phi and y0 is minus b sin phi. This is fine. And so this is wrong, this is not correct. It should be phi is equal to omega t, because if I consider the coordinate is phi, then it will relate with the angular velocity times t. So phi should be omega t, not omega is equal to phi t. Now we have the coordinate of this point mass. Next we need to look at this object, and let x is the coordinate of this object, and x is basically x0 plus L sin theta. So this is the x, and now look at the y coordinate, which is given by y, and y is basically y0, and that this height L cos theta. So I took negative sign because it is along the negative y direction, and at the end you can see this y part is entirely negative, and from here we can see that this x and y is actually expressible in terms of theta and phi variables, and therefore this theta and phi are the generalized coordinate for this entire problem. Now we have the generalized coordinates. Now we use these coordinates to find the kinetic energy of the kinetic energy and potential energy of the system. So let's start with the kinetic energy. So kinetic energy is half mv square. So v square is nothing but x dot square plus y dot square. Fine, there is no confusion on that, and we just take the x dot and y dot, and that will get and substitute it here, and that will give us the expression for kinetic energy. And this is the expression for the kinetic energy, and you can see we have phi dot, theta dot, and these are the generalized velocities for this problem. And now if I use phi is equal to omega t, then it will come down to this expression, but it is up to you whether you can stop here also, or you can consider this one also. And next what we need to do, we need to figure out the potential energy. What is the potential energy here? It should be like m times g into height. What is the height of this object? Is y. So mgy, and this is this y expression. Now if I again write phi as omega t, v will be this. Now I have t and v, that will give me Lagrangian. So t minus v, and this is the Lagrangian. So we have solved this problem or figure out the Lagrangian just by properly knowing the coordinate of the mass m. So in this problem we have considered only a single object. So in the next problem we will consider two objects, and which are like coupled with each other. And so let's move to the next problem. So let's start with this double pendulum problem, and it's a very common problem in the context of finding Lagrangian. And in many competitive exams, people may ask you to figure out or solve what is the Lagrangian for a double pendulum. So from this picture, it is clear that there are two pendulums where the second pendulum is attached with the bob of the first pendulum. And we consider the string lengths for both the pendulums are equal, as well as the masses for both the bobs are also equal. And let's consider theta is the angle with which the first pendulum is oscillating, and phi is the angle with which the second pendulum is oscillating with the making with the bob of the first pendulum. Fine. And now for finding Lagrangian, we need to find the coordinates for these individual objects. And before finding the coordinates, we need to fix the reference directions. So let's consider this upward direction is the positive y, and this direction is the positive x, and O is the origin. Fine. Now we focus on this first bob. So this is the x coordinate for the first bob, which is L sin theta, and y1 is the y coordinate for the first bob, and this y1 height is L cos theta, and I put a negative sign here just to make sure we are in the negative y direction. Now let's move to the second bob, and x2 is the x coordinate for the second bob, and x2 is nothing but x1 plus this distance which is L sine phi. So therefore x2 is L sine theta which is x1 plus L sine phi, and similarly we find the y2. So y2 is nothing but y1, this height is y1 plus L cos phi. So y1 is L cos theta and next height is L cos phi. I put a minus sign for the negative y direction. Now we have both the coordinates for both the pendulums, and we can see that with theta and phi we can describe this entire system. So therefore theta and phi are our generalized coordinates. Now we need to look at what are the kinetic energies and the potential energies of these individual pendulums. So let's start with the first pendulum. So this is m half m v1 square. So v1 square is x1 dot square plus x2 dot square. Fine, where x1 and x2 are the velocities along the x and y directions. So we express already x1 and y1 in terms of theta. So definitely the velocity will also occur in terms of theta dot. So this is the kinetic energy half ml square theta dot square. And next is the potential energy, which is mg into height. Height is y1 for the first pendulum, and this is the potential energy. Now let's move to the second pendulum, and we will follow the same prescription for finding kinetic and potential energy. So x2 dot square to y2 dot square, and we are writing x2 and y2 in terms of theta and phi. So the final velocity will come in terms of the final thing will come in terms of theta dot and phi dot. And similarly, we look at the potential energy which will be like mg times y2. Y2 is the height for the second bob, and this is the potential energy. Now let's look at the Lagrangian, and which is T minus V. So here we have T1, T2, V1, V2. We have all the kinetic energies and potential energies. So T1 plus T2 is the total kinetic, and V1 plus V2 is the total potential energy, and we are subtracting from each other, and that will give us the Lagrangian. So we have figured out the Lagrangian for this little bit complicated system just by finding the coordinates and following this prescription. So now we'll repeat similar type of problems for another situation. So let's move to the next problem. So our current problem is a two mass system or a two body system. In the figure you can see there are two objects. First object is a blue object of mass capital M, and the second object is a red object of mass small m, which is sitting on that first one, and both these objects are moving along this direction with some velocity, as well as the second object is also moving along this inclined plane with some other velocity, suppose. And now we need to find the Lagrangian for this entire system. So before finding the Lagrangian, we need to fix our reference directions, then we need to find the coordinates, and after that we can find potential and kinetic energies, and that will lead us to the Lagrangian. So let's fix the reference direction. So this is the positive y, and this is the positive x, and this is our origin. Another thing that we can consider here, this height. So this height will remain same throughout this problem, so let's call it h. Now we focus on this mass blue object, and x1, it is at a distance x1 at a given instant of time from the origin. So coordinate of this object is x1, and now we move to this red object whose coordinate at a given instant of time we are taking as x prime and y prime. And for finding x1 and y prime, we consider another stuff, that is from this top point the red object is at a distance x2. Now with combining x1 and x2, we can easily figure out x prime and y prime. So x prime is basically from origin to this distance, from like here to here, and which is x1 plus this distance plus x1 will give the x prime. And what is this distance? This is like x2 cos theta. And now you look at the y prime. Y prime is simple. This is like h, this is the total height minus this distance, which is x2 sine theta. Now we have all the coordinates for these different objects, and from these coordinates it is clear that with x1 and x2 we can describe this entire system. Therefore x1 and x2 are generalized coordinates. Now we can easily figure out the kinetic and the potential energies for these systems. So let's start. So this is the total kinetic energy expression. Now for just for clarity, so first term is the kinetic energy. This one is the kinetic energy of this blue object, and second term is the kinetic energy for the red object. So I'm just circling them as blue and red. So this is the these are the two kinetic energies. Now if we find the x1 dot will remain x1 dot, and if we find the x prime dot and y prime dot, then this is how this is how the expression will look like. And if we combine them, so there are three terms. The first term is representing the the first term is the kinetic energy when this kinetic energy of this both the system are moving along this direction. So that is the kinetic energy in that situation. Second term is representing the kinetic energy when this m1 is only moving along this inclined plane. And there is another term which is kind of the representing the overlap of these two velocities. So that's why the x1, x2, then there's a cos theta. Cos theta is basically the angle between the two velocities that you can see from the figure. Now, next we move to the potential energy. Potential energy is basically mg times height. So here height of this mass m is y prime, so it will be mg y prime. So we can easily figure out the kinetic and potential energy as well. Now if we combine these two, we'll find the Lagrangian. So this is our Lagrangian. So now just by finding this coordinates, we can easily figure out the Lagrangian for this system. And by using Lagrangian, one can also find out the equation of motions. So now we want to summarize our entire slides. So let's go to the summary. Now, if I want to summarize these entire slides, then one thing we can say, we have figured out a prescription for finding Lagrangian. And what is that prescription? And if we now split it into steps, then the first step is to find the coordinate of the individual systems. And that step will lead us to the potential energy. And now, if we take another step, just find the time derivative of these coordinates that will give the kinetic energy. Now, if I combine kinetic and potential energy together, that will give me the Lagrangian. And this is a kind of algorithm or flowchart for finding the Lagrangian. Now, if you like this video, please share and subscribe. Thank you for your attention.